You are using the computer audio. Okay.
Okay.
Start video. Well, it's kind of early, but I guess we could get started. What do you think?
Yeah.
Well, Shazam.
Nobody's even there.
Well, maybe they'll show up in a minute.
What happened?
I don't think anything happened.
And if you need my computer,
No, this is going to be fine, I'm sure.
what is this?
Oh, no.
So the rest they can't simplify.
I think the rest you're stuck with them. They don't simplify.
So just put one here, because that's
Yeah,
one hole.
10 chances one. Yeah, good going. A download should start automatically in a few seconds. If not, download here.
I don't know what's wrong with it. Want me to call Mama?
Well, not yet. I haven't panicked yet.
Wait, click Zoom. There's Zoom there.
Click this one.
Yeah.
Your meeting will begin soon.
That's your meeting.
Well, there we go. No.
No, I know what I'm doing. I know.
No.
But I was making it full screen.
How did you do that?
See these buttons?
Yeah. Oh, okay.
That, like that.
Do that again.
See these like square buttons?
Yeah.
Makes the screen bigger.
Oh, okay.
It's smaller.
Okay, well, that's pretty good. Now let's see if there's anybody that's showing up here.
Nobody's there.
Well, we need some people to show up.
It's only you, Papa.
Well, let's wait and see. We'll wait and see. Maybe they'll show up. Now let me see about my screen. If it's
Wait, what time do you start your class? 9:30?
9:30. I'm a little early. I'm 15 minutes early.
But you needed to get on early so we know what
Well,
to do.
yeah, we need to get on early. Now, I really need to move this back, I think.
Back. Here, I can help you.
Well, no, I think that makes it smaller. No.
Closer.
I need to move it forward. Okay, now just a second here. If we move it forward.
There we go.
What do you think about like that?
That's good.
That's pretty good, isn't it?
Yeah. Hello.
Yeah, that's pretty good. Okay. Now, I wonder if I should use this microphone or if
I see if they can hear you through the.
just the computer microphone.
Yeah, and if they can't hear you, then call me down.
Okay.
You might want to plug in your computer. Look at your battery.
Well, your mama said to let it run down. I'm going to let it run down a little bit more. Now, when we do, it'll go in right there.
Yeah.
But no.
But don't just don't let it die.
No, we don't want it to die. That's for sure. I'll let it run a little bit more, and then I'll plug it in.
If the computer can't, like the audio's not working that well, just call me.
Okay.
And I'll help you plug it in.
All right. Now today is Tuesday, April 28th.
Yes.
Is it the 28th?
Yes.
I think it is.
Yeah.
I think it's the 28th.
Is this your last week of school?
Yeah, this is my last week of school.
Lucky. I still 2 weeks and 1 day.
You poor kid. Oh, that's too bad.
Hey, at least I get to stay home.
Yeah, that's good.
Do school.
Okay, there's that. That was not That was not good. You know what I'm saying?
Maybe we should scoot the table
No,
back a
no,
little.
no, no. It's okay. I'll just be real careful.
Papa, maybe we shouldn't have the books right in your walk.
Yeah, yeah. I moved the books out of my way. That'll be better.
Something bad happened.
That was a near disaster, wasn't it?
We lost everything.
Yeah. Hey,
The
Yeah.
box broke.
but I think everything is okay. I lost my eraser.
Well,
Other than that,
at least we caught the computer.
yeah, yeah, you did. You caught it just in time. And this is where I'm going to plug this in here in a little while, but not yet.
Just don't knock it over.
Right,
We need the computer.
right.
Put some more.
Okay, everything's going to be okay.
Don't you need this?
And let me see what that is. I don't think so. We'll just put that in this vertical file.
Woo. That computer would have dropped. It would have broken in half.
Oh yeah, it would have broke the whole thing. Yeah, you earned your keep, buddy. You saved the day. Without you, I would be in
The computer.
I would be in heap big trouble. I tell you what we need to do. We need to put a pillow right there, so when it falls, it'll hit the pillow. Yeah, good idea. Excellent idea. There we go. It's foolproof plan. It's a fool.
And just in case
Yeah.
it goes over here.
Yeah. It's a foolproof plan. Nothing can go wrong. Now let's see if anybody showed up here. Let's see.
We'll just use all the pillows.
Nobody showed up.
Papa, now your computer's gonna be safe.
Now how am I going to walk through there without tripping though?
So
Put that sausage one back. I don't need
it's a
it.
sausage.
Yeah, just put it back. I don't need it.
But if the computer falls,
No, put that great big one there too. I'll trip over that one trying to get around. Yeah, I'll be okay now.
okay.
Okay, well, let's see. I don't need to plug anything in yet. I'm all right.
If the computer does that, well, hold on. If the computer starts rolling,
Yeah.
it will hit the
Oh, we don't want to hit that. No.
sausage.
It's a foolproof plan. Okay, well, you go don't forget your math.
Okay.
All right, if you have any more questions, you come and see me, okay?
And if you have any questions for me, or you have any
I'll call you if I need you, okay? Hmm. Well, we're recording, but none of my students have showed up yet. So that's kind of a problem. Well, that is a problem. Nobody showed up for the meeting. We had a meeting, but nobody showed up. Okay, well, wonder if I could make that bigger. To make it bigger, I'd have to move this closer, wouldn't I? Yeah. Okay, well, let's move this closer. I don't know if that's gonna move much closer. It's kind of where it's at. Well, I'm waiting for people to show up. This is strength of materials class. I was going to go over F8.2, fundamental problem 8.2. Hey, we've got a customer, Eric. Eric Jones is connecting. Good deal, Eric. All right. We have a student showing up for class. But is there anybody else showing up is the question.
Who knows?
Well, we got Eric. It's you and me right now, Eric.
Yeah, I've never been the first one.
You are. But you can hear me and I can hear you.
Yes.
I'm using the new computer that my daughter and I bought at Best Buy yesterday. And to get it, oh, there's Coy and Kylie. We got some more customers. Great. To get this thing to turn on, I've got to put my thumbprint on it. Have you ever heard of such a thing?
Yeah, I have. It's pretty new. So.
Do you have one of those?
No, I don't.
Well, I used to put in a password, but see, I don't need a password. I just need my thumbprint. Pretty weird, huh?
Yeah. That's how I unlock my phone, but not my computer.
What if somebody else puts their thumbprint on it? It won't open up?
No, it won't.
Man, that is really neat. Okay, well, hey, look, we got four of us now. Kylie, Kristen is here. Kristen, hello.
Hello, Professor Griffin. How are you this morning?
Oh, terrific. Now, if I turn away and look over here at the board and writing on the board and stuff, can you guys still hear me?
Yes, sir.
Yeah.
Man, it's the computer microphone. I don't have my old microphone, my extra one plugged in, and we're going with the computer microphone. There's
So
Caitlin.
what did you end up doing about your camera like yesterday? Did you have to borrow your daughter's computer? Or?
My daughter and I went down to Best Buy and I used my money that President Trump sent me. Did you get any money from President Trump?
Yes, sir.
I did too. I spent it on a new computer.
Nice. I haven't spent mine. Like it's just sitting in my bank account because I don't like to spend money. Because if I spend it, see, the thing is, I like to have money. And if I spend it, then I don't have it anymore. So I just don't like to buy things.
Well, but this is working.
Well, yeah, no,
it's working pretty good. Yeah. Well, it's almost 9:30. I think I want to go over this problem I told you guys to do. I gave you two problems to do, and some of you have already turned it in. I think I've graded some last night. I don't know if I graded yours. Did I grade yours, Kristen?
Sir, I haven't looked yet.
Yeah,
I did turn it in, but
Yeah.
I haven't looked to see if it was graded. I did, am I missing anything for this class?
Good question. Let me look and see. We're gonna look up Kristen here. Kristen, you're missing 7-13.
7-13?
Yeah, do it and turn it in.
Okay, I'm pretty sure I've already done that. Let me look in my sent emails
Look
to
in your
you.
thing. Yeah.
Yeah, I'll look in there.
Well, let me go over this F82 thing. We're going to talk about F82. Now, does that come out on, whoops. Hey, there's Allison. Welcome, Allison.
Yes, sir. I emailed it to you on the 2nd of April.
Okay, good for
But
you.
so I did send it to you. Let me look and see if I have where you emailed me back on that one.
Yeah, see if I gave you some points there. We'll figure it out. Okay, we're going to look at F82. And traditionally, you need to look at the left-hand member. But they've kind of got this on the right-hand member. Well, that's all right. We'll draw it. Here goes. See, they've sectioned this, and we're kind of looking at a right-hand member here. We have 400 kilonewtons. So you're going to have 400 kilonewtons. That'll be a shear force. Can you see that this will rotate clockwise? So you have to have a counterclockwise moment. And it'll be, that's 0.5 meters. So you multiply 0.5 meters by 400 and you'll get 200 kilonewton meter bending moment. There's your bending moment. And it's 200 kilonewton meters. Now that's on a right-hand section. You're supposed to do everything on a left-hand section. So let me do the left-hand section. Here we go. The left-hand section. Yeah, show me what you got there. Hey, time out. We have to do a 4th grade math problem
It
here.
says write two fractions whose sum is greater than 1. 18.
Write two fractions whose sum is greater than 1.
Mhm.
I don't know. Why don't you write maybe 2/3 and 3/5 or something, or two. How about 2/3 and 2/3? That'd be bigger than 1, wouldn't it? Try it. Okay. All right. Now we're looking at a left-hand section, but you see that shear going up there on the right-hand section? Well, it's got to go down on the left-hand section. And do you see that bending moment that's no, it's clockwise. No, that's counterclockwise on the right-hand section. Well, guess what? The bending moment on the left-hand section will be clockwise. It's Newton's third law. See, for every action, there's an equal and opposite reaction, and this bending moment is 200 kilonewton meters. Okay, now we're going to use our equations that we know and love. There's one that goes like this. That's our beloved flexure formula.
It was 4/3. Would that be a whole?
That's bigger than a whole. That's what they wanted, right?
Yeah. So would I put 1 in?
Well, yeah, I don't know. You can put 1 in the third, or just leave it 4/3. If I don't care, it's still bigger than 1. Okay, now we're going to find out the normal stress. But see, we got to know why they're talking about. Now, if you look at the picture here, I'm on page 430 in my book here. They've got a point right here that's 0.1 meters, but the whole thing is 0.3 meters. And see, this y here is the distance from the centroid. Well, the centroid's right in here in the middle. Maybe up just a tad. It's right, yeah, it's right here. This little distance here, that little distance there, that's your y. See, y is the distance from the centroid. We knew that, and it's 0.05 meters. So we just figured out y. And we know m. M is 200 kilonewton meters. Now here's something else I want you to look at. This is compressive. Now see, we're used to having compression on the top and tension on the bottom. But this is a cantilever beam. And it's going to have, believe it or not, it's going to have tension on the top, just backwards from what we're used to. And it's going to have compression on the bottom. It's a cantilever beam. If that doesn't make sense, just ask me. We got some more customers here. Coy, Gavin, Daniel, we got a good Allison. We got a great class here. Okay, now all I need here is to find this I, and I can do this problem. Now the I is just going to be 1/12 0.1 meters times 0.3 meters cubed. Okay, let me do that. And 1/12 times 0.1 times 0.3 cubed. I got an 2.25 times 10 to the minus 4 meters to the 4th. There's my moment of inertia. So look at here. I've got everything I need. Now this minus sign, don't get confused. See, the y in this case is minus because we're going down. And so you have a minus and a minus, that would come out plus, and you'd get tension. Well, that's what you would get for a normal bending load, because you have a beam and it sags in the middle and you have tension on the bottom. But see, this is a cantilever beam, and our cantilever beam is going to have tension at the top. If that bothers anybody, just speak up. Okay, well, here goes. I'm plugging all this in now. I'm going to take that I and divide it into that. And the m is 200 e to the third, and y is 0.05. In other words, you're going to have to think about this minus. It's just not an automatic kind of thing. You're going to have to think about it. Okay, well, I got 44.44 megapascal. We just figured out the that's the bending stress on that cantilever beam. That's spelled cantilever, C-A-N-T-E-L-E-V-E-R, I think. But you can look it up in the dictionary if I'm wrong, and you could get a thank you point. Okay, but now wait a minute. We got another equation to worry about. This little guy here. Now that formula has a name. It is called the shear formula. It's the shear formula. And we already know I. The T is just this thickness. It's 0.1 meters. I know it. Now the V, I know it too, because look, it's 400 kilonewtons. And on the left-hand member, shear going down is positive. All we got to do is figure out this Q. If we could get that Q thing, we could get the shear stress at this location they want. They want it right here. Okay, well, here's how you do the Q thing. I've shown you this before. What you do is you draw a line through the place where you want to find your shear stress. And here's our line. There you go. And then you color everything below the line. And that's what I'm doing now. I colored everything below the line. Okay. And then you measure from the centroid of the whole piece to the center of that colored area. Well, from there to there is 0.1 meter. So it's 0.1 meter. You go from centroid to centroid, the centroid of your colored piece to the centroid of your whole thing. You get 0.1 meter times the area of what's below the line. Well, that's 0.1 meter times 0.1 meter. And so you'll get a Q of 0.1 cubed. I can do that. I'm getting 1 times 10 to the minus 3 meters cubed. We just figured out Q. It has a name. It's called the first moment of area. Okay, I'm going to plug I know everything here. I'm going to plug it all in now. Here goes. V is 400 e to the third. I is 2.25 e to the minus 4. And T is 0.1. Okay, here's what I'm getting. I'm getting shear stress is 17 point bunch of sevens megapascal. Now we're going to draw the Morse circle and find out the maximum stress at that location. I tell you what we've got here. We've got the shear stress and the normal stress in the principal directions, the X direction, you know, and the XY or the Y direction. But that might not be the maximum. We're going to use a Morse circle and get the maximum now. Here goes. But before we do that, anybody have a question on any little old thing that we've done so far? You can still hear me, right? I see Heath just showed up. Hey, Heath.
Yeah, we can still hear.
You guys can hear me.
Yes,
Fabulous.
Professor.
Good deal. Nobody has any questions? You're happy with this? We're doing fundamental problem 8.2. You've worked on it. You know what? I think I would be smart to plug in this this battery charger thingy. Let me do that. That might be smart. I'm plugging in the battery charger now. There we go. Okay. All right, we're going to do the Morse circle unless you have a question. I just need some room to do it. So I'm going to have to sacrifice some stuff. Say goodbye to a bunch of this stuff because we need the space. All right. Now the way you do the Morse circle, we've done it many times before. I've got a ruler here. I could actually measure it. So here goes. I'm going to actually measure this. First, you draw the normal force. The normal stress. First, you draw the normal stress axis. There we go. And then you draw the shear stress axis. Okay. There we go, shear stress axis. And then what you do is, I really should draw the stress element so you can see this better. What we have here is your normal stress is 44 megapascals. And then you don't have any, there is no normal stress in the Y, but you do have shear stress of 17. You have a shear stress in the XY direction of 17.7 megapascal. Go ahead, I'm listening.
Isn't it supposed to be compression for the normal stress?
Yeah, it's compression because it's a cantilever beam. Thank you for asking, Toy. Oh, he's not asking, he's getting a thank you point. Toy just got a honking thank you point because it's compression, isn't it, Coy?
It's sure.
Yeah, good going. Proud of you. You're absolutely right. Okay. All right, now let's see if we can do this. Well, if it's compression, it's got to go over here to the left. Dang, I should have made this. Let me make this over here a little bit further so I'll have more room to play with here. Yeah, Coy's on the ball there. He is on the ball. Okay, so what we're going to do is we're going to go to the left because it's compression, 44. Well, I could use inches. That'd work. There's 44 right there. Now that's going down, so I got to go up 17. Well, 17 is, I'm using inches, is about like that. So that puts me right there. Now, I went up 17 something, and this is 44.4. Now I went up there, so I got to go down here 17. Okay, well, I can do that. It puts me about there. And now, see, that's 17.7 going down to there. This is 44.4. And now I'm going to draw the diameter of my Morse circle. Ta-da, there you have it. And you know what? This is 22.2. That's 22.2. And so is that. That's 22.2. And now we're going to do the Morse circle. What I need to do, though, is I need to go 22.2 squared, 17.7 squared, square root. That'll give me the radius of the Mohr's circle. Let me do that. Here, I can sit back down now. Okay, we're going to get the radius of the Mohr's circle now. We have 22.2 squared plus 17.7 squared, square root, 28.4. This radius here is 28.4. They're megapascal. And now we're going to draw the Mohr's circle. Here goes. 28. Oh, I'll use my inches again. 28.4. Let's see, that'll put me right here. I'll get a few more spots here. 28.4. 28.4. Around in there. 28.4. 28.4. Yeah, that's pretty good. Now I'm going to draw my Mohr's circle. Here goes. Oops. There we go. We now have our Mohr's circle. Now, the most important point on this Mohr's circle is right there. And you know what that is? That's compressive. It's compressive normal stress, isn't it? And I can tell you how big it is. See, if this is 22.2 and you add 28.4 to it, let me do that. 28.4, 6, 10, 50.6. The maximum compressive stress is 50.6 megapascals. Well, that's bigger than 44, isn't it? That's pretty significant. Now, you also have a little bit of tensile stress at that location. We could figure that out. The tensile stress at that location, that's tensile caused by tension. The thing is, it's not along the X direction, though. It's at an angle. And so you can get the angle. The angle, remember, this is your anchor point here. That's where we got our first anchor point there. You can either go a negative angle to get it, or you can go all the way around a positive angle. You can even get the angle, but I'll tell you what it is. For the tensile stress, it is 22.2 minus 28.4. Now, if you do that, if you take a positive 22.2 and a minus 28.4, I think you get 6.2, don't you? Did I do that right? I think so. So the tensile stress is a positive 6.2 megapascals. And if you wanted the angle, you can get it. I think what I would do is would go, all angles are measured from here, from this anchor point. I would go all the way around here like that to get that angle. Now that angle, I'm going to have to think about this a minute. If you take the arctangent of 17.7 over 22.2, that'll be this little angle in here. Let me get that. 17.7 divided by 22.2, and then you hit the arctangent button. It's 38 something degrees. This little angle right here is 38.6 degrees. So this angle here, you'd have to add 180 to it. And so that would be 218.6 degrees. That's 2 theta is 218.6. So theta, divide that, and let's see, yeah, you divide that by 2 to get theta. And so this angle right here where you get your tensile stress is 109 degrees, 109.3 degrees. So you can get not only the compression and the tension maximum values, but you can get the orientations also. Well, there's that problem. And a lot of you, I was proud of you, you turned it in, and we gave you some points there in the grade book. And I want to move on to the next exciting topic now. But does anyone have any comments or questions before we move on? Well, nobody said anything, so we're going to move on, okay?
So it's called,
Go ahead.
I would like to ask that the one is the tensile stress on the square diagram, like the diagram. When is it going down?
The shear stress. Why is the shear stress going down?
Yes.
The shear stress is going down because, see, I erased it. I need a little room here to show you. Let me make some room here, Coy. Remember, we had a right-hand section and a left-hand section. And we had forces doing this. But on the left-hand section, I didn't draw that very good. On the left-hand section, we had forces doing this. Now, presumably, at this fixed connection over here, there will be a force going up. That makes sense.
Yes.
Now, when you look at, you always do shear with a left-hand section. That's a left-hand section. This is a right-hand section. And you're supposed to use a left-hand section. Okay, the shear is going down, and that's how come our shear stress is going down.
Oh, okay. Thank you.
You are so very welcome. Anybody else? Okay. Well, we're going to study our last topic now. It's sad, but our time together is coming to an end. We just have this week, and then I'm going to give you a final, and that'll be fun for me to grade. But the last topic is buckling. We are going to study buckling, the buckling of columns. And it's in your book. I think it's a very important topic because there's been some disasters when columns have buckled and things have collapsed and people have died. The chapter is, let me see if I can find it here. Okay, I'm looking for. Yeah, here we go. This is chapter 13. Now, I wish we were together where I could show you an actual column and we would load it under compression until we reached a place where it buckled. But I don't, it's sort of like, I've got this ruler here. It's a 1 foot ruler. And if I was able to push on this ruler hard enough, it would buckle. But I can't, I'm not strong enough. But see, if I was, it would start to bend if I pushed hard enough. It's called buckling. And a Swiss mathematician by the name of Euler, I bet you've heard about him in mathematics. He came up with some fantastic equations. The most famous equation he ever came up with was this one here. Now, don't quote me. I'm a little bit rusty, but I think that's Euler's famous equation. And what he's got here is a wonderful combination of mathematical terms. He's got pi. We all know about pi. And he's got e, the base of the natural logarithms. That's important to us. And I don't know if you remember, but I is the square root of -1. It's the imaginary number. And when I tell you what, when Euler came up with that one afternoon, don't you know, he celebrated. He probably went out and had a picnic after that. That was a big deal for him. I bet he was very happy. But we're not doing that equation. That's one of his important equations. We are doing a different one, and it's called the Euler-Lode equation, or the critical load equation. This book here calls it both, I think, but it's called the critical load the critical load for buckling. Now, it's derived in your book, and you could read about it. It's on page, I'm looking on page 667 right now.
Hey, Dad.
Yeah, hey.
Hey, there's a bad glare on your board, and it's blurry.
Oh, there's a bad glare.
Yeah, I think you need to set the computer on something, like something taller.
Put it on something taller.
Yeah.
How about a book or something? How would that be?
Yeah, and maybe scoot the board a little bit closer.
Okay, there's a bad glare. All right. Now let's see what we can do here. Hang on a minute. What if I turn the board slightly sideways? Does that help?
No.
No, that didn't help any. Okay. Well, let's see what I can do. I'll find some books or something and prop it up. Let's see. Hang on. We have our ways. We have our ways to fix things around here. But I think they can hear me.
Yeah, you can hear you just fine. It just you can't see the board very good.
Right. Can't see the board very good. Dang it. Does that help any?
Do you have the curtain open behind on the window, like by the
Mm.
window?
No, it's closed.
Just have a really bad glare. You can see the computer and the board.
Yeah, I can see the computer in the board. I sure can. Yeah, but that didn't help
Can
any.
you? No, can you move the board a little bit closer?
Yeah, we could. We can always move it closer. I might have to stand up in order to write anything. This chair is really a bit awkward. But here, we'll move everything closer. How's that? Is that better?
Scoot it to the left a little bit,
You mean like?
or
like,
scoot your computer to the right.
oh, I could scoot my computer to the right? You mean
Sorry.
like, how's that?
Your left.
My left, okay. What do you think?
It's a little bit better.
You know, I think it is a little bit better. Well, should I go on with my wonderful lecture then?
Yeah, I mean, the only part they might not be able to see is whatever you write in the glare of the computer.
Okay, well, I don't know if I can help that, but we'll tough it out.
Yeah.
Now, can you students all hear? That was the voice of my wonderful daughter. Did you hear her?
Yes, sir.
Good. Yeah, that's my wonderful 29-year-old daughter. She's about the age of a lot of you guys. I bet some of you are 29. Some of you, or maybe some of you are even older than that.
Yeah, some of us are definitely older than that.
Well, I think there's some of you that are younger than that. Now that's my youngest daughter. My oldest daughter is, I think she's 51. I'll have to stop and think. Yeah, she's 51. Anyway, we got to get back to our Euler's critical load equation for buckling, and here it is. And we're going to give it now. Let me see if I can move this chair back just a tad here. Okay, it goes like this. The critical load, it's derived in your book. Yeah, gosh, that's right in the middle of that glare, isn't it? Well, I can't help it. It's in the middle of the glare. We're just going to have to be brave and tough it out. What the heck was that? Okay, you all know what the modulus of elasticity is, and you all know what the moment of inertia is. The length is just the length of your column. See if this is your column, and that's the length of it. Now this critical load is compressive always. You don't get buckling with tension. Buckling is caused with compression. And this is the critical load. At that critical load, if you exceed that, the column will buckle, and it'll kind of go like this. See, it'll go like that. It'll buckle, and of course, once it starts to buckle, the whole thing comes crashing down. But you understand all of these terms here. There's a slight refinement on that equation. Let me show you, and then we'll work some problems. And the equation can be can be written with a factor here. It's called the effective length factor. This K is called the effective length factor. And if you have what you call pin supports, if these are just smooth pins at both ends, the K is equal to 1. But there's other kind of supports. There's there's pin supports, and there's fixed ends, for example. Fixed. If you have fixed supports, let me see if I can try to draw for you a fixed support. That would be like if you had, here's your column, and you weld this. You put a weld in here, and so it cannot turn at any kind of angle. Remember, buckling, you're doing that. See, it's like you have a pin here and it can move around the pin. But if that's welded real good, it can't. The bottom is going to be perpendicular. See, it's perpendicular. And so if these are both what they call fixed connections, if you have a fixed connection at the top and a fixed connection at the bottom, the effective, what they call the effective length factor is 0.5. So you'd have to put a 0.5 in here. Now, if you have one end that's pinned, let's do that. If you had one end that's pinned, put a smooth pin there, and see that allows that to kind of rotate, but this can't. This has to remain perpendicular. If you have one end that's fixed and the other end that's pinned, then the K is equal to 0.7. I'm getting this out of the book. It's on page 675. So there's your Euler equation for buckling. They derive it. You can read the derivation. This guy, man, he lived a couple of hundred years ago and he came up with this. Man, he must have been smart. You know what? He must have been a smart guy.
He's the guy who came up with a lot of infinite sums and series. That
Yeah.
stuff's beyond my.
Yeah, I think I vaguely remember that from taking math in school many years ago. But it's all right there in your book and you can read it. But we're going to work some problems. Okay, here it goes. Okay. Let me make a little room here and then we'll work some problems. We got our equation now. We know we're talking about buckling. We know it's important because we don't want structures to collapse and come crashing down. Years ago, my wife and I went to Kansas City. I had to take an exam. And we went to this hotel. It was a beautiful hotel. I forget the name of it, but it's the one that came crashing down a couple of weeks later in Kansas City. You might have read about it. I think people died. They had to get cadaver dogs to find them in the rubble. It was awful. My wife and I were there a couple of weeks before it happened. It's a beautiful place. It had a waterfall in the lobby. Makes me nervous when the computer goes ding, ding, dong, but I think I'm okay. But the column failed and the whole structure came crashing down. Okay, well, we're going to work a problem now. Now this one is F13.5. Okay. We're going to work problem F13.5. And they have a it's a 3-4-5. Oh, you guys love those 3-4-5s, don't you? Well, why don't I draw that to scale? Let me draw it to scale. Here goes. 3-4-5. I guess I could use 4 inches, huh? Yeah, that'd be all right. 3-4-5. I don't know. I guess so. Okay. I think we want the 3 up here, don't we? Am I doing this right? The 3 and 4. Does it go like that? Wait just a minute. I'm not good with 3D stuff. Or 2D in this case. Oh, I got it going the wrong way, don't I? Yeah. Okay. Well, let me get it right. Hang on a minute. We want the 3 here. And then we'll draw this here. Yeah, now we have a 3-4-5. Okay. I actually did that to scale. And we're looking at F, fundamental problem 13.5. Do they tell you what the P is? Oh, we have to find the P. Oh, that's a dirty trick. We're going to have to find, there's a P right here, and we don't know what it is. But we'll label this stuff. Now this is not a member. This is just a distance. It's 3 feet, 5 feet, 4 feet. We know this angle. It's 3687. You memorized that, haven't you? It's 3687. That angle there is 5313. We don't know what that P is, but we do know it's A992 steel. And in the back, we're going to look it up.
What
In the
does
back-
it mean when it says take FS equals 2 against buckling?
And we're going to have a factor of safety of 2. We'll write that down. That's good. Now help me look up A992. And it says here that the modulus of elasticity is 29 KSI. See if you can find that in the back flap of your book. That's the modulus of elasticity for that particular kind of steel. Structural, it's a type of structural steel. All right, now let me keep reading here. Oh, the diameter. These are circular rods, solid rods of 2-inch diameter. Let me write that down someplace. 2-inch.
Professor Griffin,
Yeah.
it says the modulus of elasticity is 10 to the third KSI. So wouldn't it be MSI?
I'm absolutely wrong. You are absolutely right. It's 29 MSI. Honkin, thank you. Point. Now, who was that? Was that Eric?
Yes.
Good going, Eric. Proud of you, man. I was going to get the wrong answer, Eric, but now we're going to get the right answer. If anybody doesn't know what Eric's talking about, just speak up and we'll explain it. Okay, well, this member here is going to be under compression. That 4-foot member is going to be under compression, but this 5-foot member is going to be under tension. Tension members don't buckle, so we don't need to worry about that. But the AC could buckle. If that P is strong enough, AC will buckle. Now, we're going to calculate the critical load for AC. And Euler's equation goes like this. And these are both pin connected. A is a smooth pin. C is a smooth pin. So there's no effective link thing to worry about there. So let's go ahead and get it. Let's see. This is 29 MSI. And the length, now you'll discover it's going to have to be in inches to work. So what's 4 times 12? 48. But it's squared. See, it's squared. Now we need the I. We're going to have to figure the moment of inertia. Well, if it's a 2-inch diameter, we can do that. It's, let me think, it's 1/4 pi r to the 4th. Look in the front flap of your book. Do you see where it says 1/4 pi r to the 4th? That's how you find the moment of inertia for the circle. Okay. Well, I'm going to do that. Here goes. 1/4 times pi times 2 inches. Wait a minute. Oh, that's going to be 1 inch, isn't it? Because the radius is 1 inch if the diameter is 2 inches. Well, I'm through. Times 1 to the 4th. Okay, I'm through. I'm getting 0.61685 inches to the 4th. Double check me on that. So we just figured this out. And what's that equal sign doing there? That's not right. This should be pi squared times 29 MSI times I, which we have.
I got a
48
different value for I.
Say that again, please.
I got a different value for I.
Thank you. Let me try it again. I must have done something wrong. Thank you so very much. I didn't get that. Now who was that just spoke up?
Eric.
Eric, look at you. You got 2 thank you points here today already. Well, I'll round that off. Hey, Eric, did you get 0.7854?
Yes.
Yay, good deal. All right. Now plug this in and we're going to get the critical load that would buckle AC. Here goes. All right. Times 29 e to the 6th times pi squared divided by 48 squared. Okay, I got an answer. It's pretty humongous. I'm getting a critical load for buckling of 97 point, we could round it off. It would be kilonewtons, wouldn't it? Kilonewton. Wait a minute. No. Hey, nobody gets a thank you point. I caught that. It would be 97.6 kips. Because we're in English, senor. Hey, we're in English. We're talking inches and pounds, aren't we? Well, did anybody else get 97.6 kips?
I did.
I heard one person did. I bet that's right. Okay. Now what? Well, if that's the force that would cause a problem, when we get all through, we'll talk about this factor of safety. Let's just go ahead with this critical load, and let's look at A. Let's look at pin A. Here's pin A, and we think we have a compressive force horizontal on A of 97.6 kips, and a tension force at the 3687 going this way. I don't know what to call it. We could call it maybe, how about FAB might be a nice name. And then we have P. See, P is what they're after. This is called method of pins. I know you've done it before. The sum of these forces acting on that pin A must be 0. Okay, well, let's do the forces in the x direction. Now, in the x direction, there's some room over here. There's a component going and to the right of FAB cosine 3687. See, it's going to the right. Then we have minus the 97.6 equals 0. Hey, we can solve for that. We can solve for the tension in AB. That's not what they wanted, but we're going to solve for it anyway. Here goes. I'm going to solve for it now. So I'm doing that now. There's an equation. There's only one unknown. We can do this. I'm getting FAB is 121.9 kilopounds. But I'm going to wait till I hear an from the crowd. And I'm going to try to
That's
find
all right.
my water bottle. Here it is. Anybody get that?
I did.
Yay, there's one of us, two of us.
What I got.
Yay, there's another student. But see, that's not what we want. What we want is this load P that will cause buckling of AC. Well, now what we're going to do is we're going to do the sum of the forces. See here, you know what this was? This was the sum of the forces in the x direction has to be 0 on pin A. Now we're going to do the sum of the forces in the x direction. No, I mean in the y direction has to be 0 on pin A. Well, in the y direction, we've got the FAB. What is it? 121.9 kips times the sine of 3687 minus P is 0. There's our y equation on pin A. And we can solve it for P. Here we go. I'm going to solve it now. All right, I'm solving it. And here's what I'm getting. If you put a force P of 73 point, round it off, 2 kips, AC will buckle. But they have a factor of safety of 2. Now, remember what factor of safety is. What it is your failure load over your allowed load. So this is our failure load right here. We just figured the failure load. If you put 73 kips on this and pull down on that thing, AC buckles. But the allowed load, if you solve this, see if you know what this is, and you know what that is, you can solve it. It'll just be half. What's half of 73.2? 36.6. Okay, guys, the answer book should say P is 36.2 kips for the what they call the allowed load. And now let's look it up. This is a fundamental problem. I love these. They show you how to do them in the back. I'm going to go back in the back and find the F13.5. F13.5. Okay. F13.5. F13.5. Is that what we're doing? Yeah. F13.5. Okay, I'm on the wrong chapter here. 13.5. Okay, now they said F13.5. They say P is 36.6. Now, wait a minute. The book got 36.6. They got 36.6, and we got 36.2. I wonder where we went astray here. Huh.
I think that you might have divided wrong or something. It should 73.2 divided by 2 equals 36.6.
That's my problem. I don't know how to divide by 2. Let me try that again. I'm going to take 73.2 and I'm going to divide by 2. And by Jove, it's 36.6. If you know how to divide by 2 correctly, we'll get 36.6. Good deal. Now whose voice was that?
Eric?
Somebody else start earning these thank you points besides Eric. He's got too many already. All right, well, that was a load of fun. Now we're going to do another one here in a minute. But why don't you go ahead and ask me anything you want there. I'll answer your question. If anybody has a question, now's the time, because I'm going to erase all this and we're going to do a different one. We got time to do another problem. Well, okay. Nobody said anything. So say goodbye to fundamental problem 13.5, and we're going to do a different problem now. On buckling. There was another buckling disaster in Joplin years ago. I forget the name of the hotel. It came crashing down too. Some of you might have heard of it. Okay, now this is the one we're going to do now. This is, let me give you a homework problem. Do this for homework. Don't turn it in. I'm adding up everybody's homework and I'll put it on Blackboard soon, muy pronto. You'll know what your homework score is. But do this one because we'll talk about it on Thursday. It's 13.13-3. It's on page 679. And I want you to do that for homework, but together we're going to do problem 13.7 right now. Here goes. We're going to do 13.7. Now they have a W12 by 50. It's called a wide flange beam, W12 by 50. And we're going to look that up in the back. Go to the back. I think it's Appendix C. I'm not sure. But there's Appendix A, Appendix B. I think it's Appendix C, W12 by 50. Trying to find it here. W12 by 50. No, it's Appendix B, isn't it? Yeah. W12. Yeah, there it is. I'm in Appendix B. I'm on page 807. This is what they call a wide flange beam. And it says here the depth is 12.19. Here, I'll draw you a picture of it. The actual, what they call depth, is 12.19 inches. 12.19 inches. Well, you see that 12 there? They just sort of rounded it off. And that's the common name for it. It's about a foot tall is what it is. That's pretty heavy. Now the weight per pound is got lost here, is 50. It's if you went back here and took a foot of it, an artist's rendition here. Yeah, pretty good artwork, don't you think? Isn't that great? See, if you took a 1 foot if you cut this and had 1 foot, it would weigh 50 pounds. That's how much it would weigh. It's 50 pounds per foot. That's what the 50 stands for. See, the 12 stands for how tall it is, roughly, and the 50 tells you it's 50 pounds per foot. The wide means it's a wide flange beam. It's not a channel. See, channels are kind of deals like this here. There's things like that called channels. There's all kinds of things, but this one here is what they call a wide flange beam. All right. Now, what we need to know is we need to know the moment of inertia. Now, if you come over here at the W12 by 50, they have 2 of them. We want the smallest one, because the smallest one is the way it's going to it's going to buckle, and it is 56.3. They have 2 different moments of inertia there, but the one we want is 56.3 inches to the 4th. I happen to be on page 807. Can you find it?
Yes, sir.
Great. And now let me show you the difference between those 2 moments of inertia. I've got a meter stick here. I don't know if you can see this, but we'll try. I've got a meter stick here, and the meter stick is pretty easy to bend this way. See how I'm bending it this way? I'm bending it this way. Yeah, you can see it, but it's real hard to bend this way. I'm trying, but it won't bend, because if this meter stick buckles, it's not going to buckle this way. It's going to buckle this way. This cross section has two different moments of inertia, just like the meter stick does. And the way it's going to buckle, it's going to buckle along this axis here. See the y-axis, that's the way it's going to buckle. It's not going to buckle along the x-axis. Just remember, well, let's write our equation. The equation goes like this. This is your Euler equation. You want to have the smallest moment of inertia because that'll give you the smallest critical load that will cause it to buckle. You're not going to, if you have a bigger moment of inertia, it will have buckled long before on that other axis before you ever get to that the bigger moment of inertia. I don't know if that made sense, but read the book. Okay. Now we're going to find, I think what we're going to find is that critical load. Let me read it and see what they want us to do. If you tuned in late, we are doing problem 13.7. It's on page 80. No, it's on page 680. It's on page 680. It's problem 13.7, and it says it has a length of 20 feet. Okay, well, let me make note of that. The length is 20 feet. Is subjected to an axial load of 150 kips. Okay, well, they're going to give us this. Look at here. They're going to give us the L, and they're going to give us the critical load. The critical load is 150 kip. Okay, and let me keep reading. They want to find the factor of safety. The ends are assumed pin supported. So this K thing, this effective length is just 1. So there's our equation. Now we're going to need to know E, but didn't we just do that? I have a sense of deja vu here.
It was 29 MSI.
Yeah, thanks to one of my excellent students. E is 29 MSI. So we have that. We have this because we just looked it up. Yeah. Hey, we got it made. I think that's all there is to it. Boy, that was easy. Let me see. Is there something I'm missing? No. Oh, there's a factor of safety. Oh, we have to find the factor of safety. Okay, well, we will. First, let me find the critical load. This will be the failure load. All right, here goes. I'm going to find it now. Failure load will be pi squared times E, which is 29 e to the 6 times 56.3. You know what? I wonder if our units are going to be okay. They'll be okay. They'll be okay if you put this in inches. What's 20 times 12? Would it be 240? I did that in my head. That's dangerous.
Yes, that's right.
2,400.
It's not. It's 2,400, isn't it? I didn't finish that. I was still thinking. You don't get a thank you point.
12 is 240.
Or is it 240? Which is it? I don't know. Let me try it. Let's see, 20 times 12. No, I had it right in the first place. It's 240 inches, isn't it?
Sorry.
You're forgiven. I was going to give you a thank you point anyway, but you were wrong. You don't get one. Okay. So here, let's put all this stuff in here. Here we go now. I got to start over. Pi squared times 29 e to the 6 divided by 240 squared. Well, I'm getting 49.69 pounds. I think that's right.
I didn't get that.
Let me do it again. Just a minute. Let me do it again. Pi squared times 29 e to the 6 divided by 240 squared. I'm getting 49.69. How about you guys?
Did you multiply by 56.3?
Did I forget to do that? I might have. I think I did. Let me try again here. Pi squared times 29 e to the 6 times 56.3. I might have forgot that. Divided by 240 squared. By Jove, that's wrong. And I owe somebody. Who was that? Was that Eric again?
Yes.
Eric really, he deserves something. I don't know what. Maybe a cupcake or something. He deserves something. Okay, I'm getting a humongous number of 279 kips. Is anybody getting 279.8 kips?
That's what I got.
Anybody
sir.
else? Yeah,
Yes, sir.
that's it. Okay, hey, we just figured that. But now wait a minute. They want us to find the factor of safety. Now, some books call it the factor of safety, and some books call it the safety factor. It's the same thing. What it is, it's the failure load, which we have. That's it. That's the failure load divided by your allowable load. Well, we have both of those. They said they're going to put. Okay, I got lost here. They said they're going to put 150 kips on it. So this is 150 kips. And this is 279.8 kips. And so the factor of safety is, take 279.8 and divide by 150. I'm getting 1.87 if you round it off. It doesn't have units. It's just a factor of safety. Let's see how we did. What was this, 13.7? I want to see what they said it was. I'm looking up their answer now. And they said the answer is $1.87. That's what the book says. Yay, we did good. We got the factor of safety. I'll tell you a little something about the factor of safety. On some components of airplanes, the factor of safety sometimes can be dang close to 1. You think, well, the bigger the factor of safety, the safer you are, of course. But here's the problem. If you make the factor of safety too big, you have to make something really strong and heavy and clunky. And if you have an airplane and it's made of components that are really strong and heavy and clunky, it's hard for the airplane to get off the ground. You want the airplane to be as light as possible, but still strong. But you don't want it falling out of the sky. So many of the components in aircraft are they have pretty small factor of safety. It's nice to know that it's never going to break, but hey, if the thing can't get off the ground, it's not a very good airplane. Okay, guys, well, we've had a load of fun together, and I've given you a homework problem to work here. Don't turn it in. I'm going to finish grading the homework that you've turned in and give you your homework scores, and you'll know what they are on Blackboard. Does anybody
Sir,
have any last questions or comments?
I checked my emails where you emailed me back, and you emailed me back the next day and gave me a 4 on the
Shazam.
7-13.
Shazam. That's Kristen. It's recorded. Got it.
Thank you. Thank you.
Thank you. Anybody else comment or question on any little thing? Well, okay. I think I'm going
Sorry,
to.
I did have a question. But
Yes,
not
go
over
ahead.
This homework.
Mhm.
What sections do we need to really focus on for the final?
Ooh, that is a good
I guess-
question. Excellent question. Well, we need to know how
You
to
know-
find moments of inertia. For
I was
sure.
going to say there's probably too many to get off the top of your head. So could you?
Well,
post
you know
sections?
that's going to be on the test. And
Well, we
in
know
the-
this because
Yeah, go ahead.
I was going to say we know this is going to be on the exam because it was just covered. But what about
Yeah.
the ones that weren't recorded and then uploaded to YouTube?
Yeah, you've got my wonderful lectures that you can watch over and over. One
There
of the
were
things
a few that weren't recorded.
Oh, yeah. I don't know what to tell you about those that didn't get recorded, but I guess there were some before we got the hang of it. But you have to know how to find the centroid too. And you have to know how to use these equations, what they call the flexure formula. You know this one here. And the shear formula. That Q thing really gives students trouble. You know there's going to be a question on those. Go back over the homework we've done, the stuff we've done on our wonderful lectures.
Just
That'll help.
probably
It's an
gonna-
open book. I think you have 3 days to do it, or at least 48 hours. So you can dig into your book and do a real fine job for me.
When will you post the test and when is it due?
Sunday night, I'm going to post it, and it'll be due Wednesday night.
All right, sounds good.
Sounds good to me. Anybody else? Well, I'm going to say
The
goodbye.
last homework. Oh, sorry. The
Yeah,
last
go ahead.
homework isn't available for viewing that we uploaded.
Do you know which one that was? Was that the Moore circle thing?
It was the most recent one due Sunday.
Yeah, was it 821?
I thought it was F82 and then
It was
821.
F8-2 and 821.
Yeah. I graded that. A lot of you did that. Most of everybody turned that in. They did a fine. 90% of you did great on 821. The answers are in the back. Now, what was your question about it?
It wasn't a question. It's just not available for viewing on Blackboard.
Oh, yeah. Yeah. If I was on the ball, I would have
Oh.
that on Blackboard for
Never
you.
mind. It's available for viewing through the grades.
Yeah, you should get a grade on it. Well, okay. I think I'm going to sign off here unless somebody else wanted to say something. Okay, well, thanks so much. And Eric gets the prize today for the most thank you points. All right, I'll see you guys on Thursday. Fair enough?
See you in a couple hours.
See you in a couple hours. Yeah. Well, ta-ta for now.
Have a good,
Bye.
have a good rest of the day.